Welcome to the final installment of my Transformations video series. The Part 5 video series is about using matrices to perform the transformations. In this installment, Part D, we'll look at composite transformations as well as a proof that we need in the rotation case, where we were using rotation of the coordinate system to obtain coordinates that we could then rotate back to the original system as an equivalent of the transformation, and we will prove that. So the transformations that we've talked about in this entire series is translation by matrix addition, reflection, and rotation by matrix multiplication. The translation is simply the sum of the vectors as shown, and the rotation transformation matrices can be derived from a generalized case where theta is set equal to the angle that you'd like, either 90 degrees minus in the clockwise rotation or 90 degrees plus in the counterclockwise direction, or 180 degrees. And then we derive three matrices that handle the reflections over the axes as well as the line y equals x. In the case of composite transformations, in the original coordinate rule examples, we showed that the operations of the transformations matter, that these operations tend not to be commutative, that if you perform the transformations in the opposite order, for instance, you will not end up with the same answer. And the example I gave was true, but that was only because I had used a translation as part of the three systems that I was doing. The transformation operations in the middle that are handled by matrix multiplication, which were rotation and reflection, that's where matrix multiplication is not commutative. But unfortunately, in the example that I gave using the rotation of 180 degrees, the direction reflection rotated by 180 degrees versus rotation of 180 degrees first, followed by the reflection, ended up with the same value. And you can see that by looking at the matrix multiplications down below. We ended up with a minus 7, 4 for the same vector. So sometimes a stopped clock is right twice a day, but in general you can't count on that. You can't count on matrix multiplication to be commutative. So I gave the example of the rotation by 90 degrees. So on the right hand side we have reflection of the x-axis first, again reading from right to left, followed by the rotation of 90 degrees as not being equal to the rotation of 90 degrees, followed by the reflection over the x-axis. In this case, AB gives you one coordinate, BA gives you another one. So let's look at that first. Let's look at the reflection over the x-axis, followed by the rotation of 90 degrees. This is the original pizza is the gray ghost up in quadrant 1. The reflection over the x-axis is the colored light line version down in quadrant 4. We then reflect that over the x-axis, we get a figure like this. Taking away the original figure, we can see it more clearly. Now looking at the composite transformation in the other order, we're going to rotate 90 degrees and then reflect over the x-axis. When we do that, the original in the gray ghost up in quadrant 1 first gets rotated 90 degrees into quadrant 2 and is then reflected over the x-axis. And you can see that that's a different position entirely of the figure. So the composite transformations, you cannot rely on them being commutative, though occasionally with a stop clock is right twice a day, they can be. So we need a necessary proof of when we can use the transition matrix coming from an old rotated coordinate or a new rotated coordinate system back to the old coordinate system. When can we count on that as being equal to the standard matrix of a transformation where the coordinates are reported in the old basis by rotating the point? And that case is when the rotation of the point angle is opposite that of the rotation of the coordinate axes. And that's certainly intuitive visually. We can rotate the axes 80 degrees towards the point, end up with new transformed coordinates that look like that. Once we've calculated those, we can then rotate the axis back, and the point will effectively be moved to the same coordinates reported in the old basis. So to get there, we had to derive a transformation matrix into the rotated system. That was the P inverse matrix, and we derived that in the second video series. And that handled rotation into the new rotated coordinate system. Re-rotating or unrotating the axes back returns the transition. We use a transition matrix for that P. It returns the vectors from the new basis back into the old coordinate system. And shown in blue there, that's the matrix of the transition matrix from the new basis into the old basis. So as opposed to the rotation of the point, when does the standard matrix A of the transformation Tx equals A of x rotating the point, that's also going to determine the new coordinates in the old coordinate system. And that's this effect. So when does both A and P return the coordinates into the original basis? When does A equal P? When the theta equals the opposite angle. And this is a little bit of the proof that we need for that. We want to know the case where the transition matrix from the new basis and back into the old basis is equal to the transformation matrix A in the transformation T of x equals A of x, A times x. And that's when the theta is equal to a negative phi. Phi being the rotation angle of the point, theta being the rotation angle of the axes. So starting off at number 1, if you put each old basis vector into x, you return the transformed vector for each respective column of A. Thus A will be comprised of the basis vectors of T in its columns, and the rank of A will equal the rank of T, which is the dimensions of the transformed space. In addition, there may be extra columns of A that map into, extra rows of X may map to 0 in T, and that's called the kernel, or the null space of T, any vector that maps to 0 in the new space. The A matrix is only complete if the input vectors X span the original basis. It's got to be comprised of at least one non-zero component of all of the original basis vectors. The dimension theorem dictates that the dimension of the range of T, the transformed space, is equal to the rank of T, which is equal to the rank of A. And that's equal to the column space of A. It can be no more than the dimensions of the original space, which is the row space equals the column space of A, and is less by the number of vectors that map to 0, the nullity. And an example of that, of the nullity, is when a 3D object in XYZ is mapped onto a 2D plane. The Z coordinates map to 0. The P inverse matrix maps the vectors of the old basis into the new basis coordinate system. The transition matrix moves them back. It thus returns the coordinates in the old vector basis, just like the transformation matrix A does. The transformation then can be performed in the new basis, but with a different transformation matrix coming back. And this is quite commonly done, where if you have a transformation to perform, it may be easier to do it in a transformed, into a transitioned space, into a new basis. Transition the problem into a new basis, perform the transformation that you want to do, and then transform the coordinates back. And this is of the form A prime, an alternative route for the transformation, is to transition matrix into the new basis, perform the transformation in the new basis system, and then transition the matrix back. A prime equals P inverse times A times P. And that'll be the equivalent transformation equal to AX, A prime times X. So if A equals P in that system, then the A prime equals inverse of P times P, and then times P again, which is the identity. The P inverse times P gives you the identity matrix I. So IP equals P. So in that case, the A prime equals P. The transition matrix can be used as the A prime standard matrix in the transformation Tx equals A prime. So this is the same as A equals P in the equivalent transformation T of X equals the standard transformation matrix times X. That happens when the angles are equal and opposite. So this is the case where the transformed point moves the angle down to the point in the old coordinate system. The rotation angle theta is rotating the coordinate axes to the point, drives a new set of coordinates. In this case, we're not really performing any transformation in the new space, we're just returning those coordinates back to the original system. So back to the same angle phi. And that's true when minus phi is equal to theta. So that proves that the rotation transformation can be carried out by the transition matrix from the new system to the old system once you can derive the transformations into a new basis system. This is commonly done in many fields. It's done in engineering. For example, transitioning to a stress configuration that's in the principal axis direction. So you rotate the coordinates into the principal axis direction of stress, do the transformations that you want to do, and rotate the system back. Another example is in my field in hydrogeology, we'll rotate axes into the principal component directions of hydraulic conductivity, calculate the calculations we need to do in terms of coordinates, and then rotate the coordinates back. I hope you enjoyed my series on transformations, and this last set, part 5, being all of the methods of the previous 4 videos, only this time performed by matrices. And join us for other presentations in both math and geology at Provenance Geosciences and in support of carbon negative water and energy.